Gravitation, the introduction. Earlier in our lives, we become aware of the tendency of material objects to be attracted towards the earth. Anything thrown up falls down towards the earth. Going uphill is more tiring than going downhill. Raindrops from the clouds above fall towards the earth, and there are many other such phenomena. Historically, it was an Italian physicist Galileo who recognized the fact that all bodies, irrespective of their masses, were accelerated towards the earth with a constant acceleration. It is said that he made a public experiment with bodies rolling down inclined planes and close to more the accurate value obtained later. A seemingly unrelated phenomena, observation of stars, planets, and moon, and the motion has been the subject of attention in many countries. Since the earliest of times, observation since earliest of times recognized by stars which appeared in the sky with positions unchanged year after year. The more interesting objects were planets which seemed to have regular motions against the background of stars. The earliest recorded model of planetary motions proposed by Ptolemy about 2000 years ago was a geocentric model in which all celestial bodies, stars, the sun, and the planets revolved around the earth. The motion that was thought to be possible for celestial bodies was a motion in a circle. Complicated schemes of motion were put forward by Ptolemy in order to describe the observed motion of observed motion in a circle. Complicated schemes of motion were put forward by Ptolemy in order to describe the observed motion of planets. The planets were described as moving in circles with center of the circle themselves, moving around larger circles. Similar theories were advanced by Indian astronomers some 4000 years ago. However, a more elegant model in which the sun was the center around which the planets revolved, the heliocentric model, was already mentioned by Aryabhat in 5th century AD in treatise. A thousand years later, a Polish monk named Nicholas Copernicus proposed a definitive model in which planets moved in circles around a fixed central sun. His theory was discredited by the Church, but notable amongst his supporters was Galileo, who had to face prosecution from states for his belief. It was around the same time as Galileo, a nobleman, Tycho Brahe, hailing from Denmark, spent his entire lifetime recording observations of planets with naked eye. His compiled data was analyzed later by assistant Johannes Kepler. He could extract from the data three elegant laws that now go by the name Keplers Laws. These laws were known to Newton and enabled him to make a great scientific leap in proposing his universal law of gravitation. The three laws of Kepler are stated as follows. Law of orbits. A planet moves in an elliptical orbit with the sun situated at the center of the foci of the ellipse. The law was a deviation from Copernicus' model, which allowed only circular orbits. The ellipse of which circle is a special case is a closed curve which can be drawn from simply as follows. A second law, the line that joins any point of the planet to the sun sweeps equal area in equal intervals of time. The law outcomes from the observations that planets appear to move slower when they are farther from the sun and move faster when they are nearer. The law of periods. The square of time period of revolution of a planet is proportional to the cube of a semi-major axis of ellipse traced out by the planets. So, the law of areas can be understood is a consequence of conservation of angular momentum, which is valid for any central force. A central force is such that the force on the planet is along the vector joining the Sun and the planet. Let the Sun be at the origin and let the position of momentum of the planet be denoted by r and p. Then the area swept by the planet is at an interval delta t. A is equal to 1 half r delta f, where v is a velocity, L is an angular momentum equal to r into p. As a planet goes around, hence delta A divided by delta t is constant according to the last equation. This is known as the law of areas. Gravitation is a central force, and hence the law of areas is as follows. The universal law of gravitation. Legend has said it that observing an apple falling from a tree, Newton was inspired to arrive at an explanation of terrestrial gravitation as well as Kepler's law. Newton's reasoning was that the moon revolving in an orbit of a radius was a subject to centripetal acceleration due to Earth's gravity. Am is equal to v square upon rm is equal to 4 pi r square upon rm, where v is the speed of the moon related to time t by relation v is equal to 2 pi rm upon t. The period t is about 27.3 days, and rm was already known by then to be about 3.84 into 10 raised to 8 meters. If we get a value of am much smaller than that of the value of acceleration due to gravity on the surface of the earth, this clearly shows that the force due to the earth's gravity decreases with distance. If one assumes that the gravitational force due to the earth decreases in proportion to the inverse square of the distance from the center of the earth, we will have am square is directly proportional to Rm inverse square. G is directly proportional to Re inverse of Re square, and we get G upon Am is equal to Rm square upon Re square is equal to 3600. In an agreement with the value G is equal to 9.8 meters per second and the value of Am from 8.3 equation, these observations led to Newton to propose the following universal law of gravitation. Every body in the universe attracts every other body with a force which is directly proportional to the product of the masses and is inversely proportional to the square of the distance between them. The quotation is essentially from Newton's famous treatise called Mathematical Principles of Natural Philosophy. Newton's gravitation law reads the force F on a point mass m2 due to another point mass m1 has magnitude F bar is equal to g m1 m2 upon r square. F is equal to g m1 m2 upon r square is equal to minus of g m1 m2 upon r square into r cap, where g is a universal gravitational constant and r cap is a unit vector from m1 to m2. R is equal to r2 minus r1. The gravitational force is attractive, that is, the force F is along minus r, and the force on point mass m1 due to m2 is of course minus F. By Newton's third law, thus the gravitational force on the body is due to F1 of the body to F2 due to related as F F12 is equal to minus of F21. Before we can apply the equation to objects under consideration, we have to be careful since the law refers to point masses, whereas we deal with extended objects which have an infinite size. If we deal with a collection of extended point or masses, the force on any object is the vector sum of the gravitational forces exerted by the point mass. So, gravitational constant. The value of gravitational constant g entering the universal law of gravitation can be determined experimentally, and this was the first done by English scientist Henry Cavendish in 1978. The apparatus used by him is schematically shown. The bar AB is too small with two lead spheres attached to its end. The bar is suspended from the spheres and brought close to the small ones, but on the opposite side. The bigger spheres attract the nearby small ones by using equal and opposite forces. As shown, the bigger spheres are opposite in nature, and therefore there is no net force on the bar, but only a torque which is clearly equal to F times the length of the bar, where F is the force of attraction between the big sphere. Its neighboring small sphere, due to torque, the suspended wire gets twisted till such time as restoring torque of the wire equals to the gravitational torque. If theta is the angle of twist of the suspended wire, the restoring torque is proportional to theta, equal to tau theta, where tau is the restoring couple per unit angle of twist. Tau can be measured independently by applying known torque and measuring the angle of twist. The gravitational force between the spherical balls is the same as if the masses are concentrated at the center. Thus, if D is separation between the centers of the big and its neighboring small ball M and small m, the gravitational force between the big sphere and its neighboring small ball F is equal to gm1 m2 upon d square. If L is the length of the bar AB, then the torque arising out of F is multiplied by L. Acceleration due to gravity. The Earth can be imagined to be a sphere made of a large number of concentric spheres or shells, with the smallest one at the center and the largest one at its surface. A point outside the Earth is obviously outside all the shells. Thus, all the shells exert a gravitational force at a point outside, just as if its masses are concentrated at its common center. The total mass of all the shells combined is just the mass of the Earth. Hence, a point outside the Earth is just the mass concentrated. Gravitational potential energy. We discussed earlier the notion of potential energy as being the energy stored in a body at a given position. If the position of a particle changes on account of the forces acting on it, then the change in its potential energy is just the amount of work done on the body by the force. As we had discussed earlier, forces for which the work done is independent of the path are conservative forces. Forces of gravity is conservative force, and we can calculate the potential energy arising out of this force called gravitational potential energy. Consider points close to the surface of the earth at distance from the surface much smaller than that of the radius of the earth. In such cases, the force of gravity is practically a constant equal to mg directed towards the center of the earth. If we consider a point of height h1 from the surface of the earth and another point vertically above it, height h2 from the surface of the earth, the work done for lifting the particle of mass m from the first from the first to the second position is denoted by W12 force into displacement mg into h2 minus h1. If we associate a potential energy with Wh at a point at a height h above the surface, that Wh is equal to mgh, where W is constant, then it is clear that W12 is equal to WH2 minus WH1. The work done in moving a particle is just the difference between the potential energy, final and initial positions. Observe that the constant W0 cancels out, seeing H is equal to 0 in the last equation. WH is equal to 0 is equal to WH0. H is equal to 0 means the points on the surface of the earth, and thus W0 is the potential energy on the surface of the earth. If we consider points at the arbitrary distance from the surface of the earth, the result just derived is not valid, since the assumption that gravitational energy mg is constant no longer valid. However, from our discussion, we know that a point outside the earth, the force of gravitation on a particle directed from the center of the earth is F is equal to gm1 m2 upon r square, where G is a gravitational constant, m1 m2 are basically the mass of the earth and the mass of the particle, and r is the distance of the center of the earth. We now calculate the work done in lifting a particle from r1 to r. r2 is greater than r along with the vertical path. W12 is equal to r1 minus r2 gm1 m2 upon r square. So we have calculated the potential energy at a point of a particle due to gravitational forces on it due to the earth, and it is proportional to the mass of the particle. The gravitational potential due to the gravitational force of the earth is defined as the potential force of the particle of unit mass. From the earlier discussion, we learned that gravitational potential force associated with two particles m1 and m2 is separated by a distance r, g m1 m2 upon r square. It should be noted that an isolated system of particles will have the total potential energy that equals to the sum of energies given by the above equation for all possible pairs of its constituent particles. That is an example of the application of superposition theorem. Escape speed. Escape speed. If a stone is thrown by hand, we see it falls back to the earth. Of course, using machines, we can shoot an object much greater and at a higher height. The object scales higher and higher. A natural query arises in mind is, can we throw an object with such an initial speed that it does not fall back to the earth? The principle of conservation of energy helps us understand the answer to this question. Suppose the object did reach infinity, and that its speed there was Vf. The energy of the object is the sum of the potential and kinetic energy. As observed, W1 denotes the gravitational potential energy, that is infinity, and the total energy of projectile E infinity is equal to W1 plus mvf square upon 2. Earth satellites. Earth satellites are objects which revolve around the Earth. Their motion is very similar to the motion of the planets around the Sun, and hence Keplers laws of planetary motion are equally applicable to them. In particular, their orbits around the Earth are circular and elliptical. Moon is the only natural satellite of the Earth, and with an orbit which is circular with time period approximately 27.3, which is also roughly equal to the rotational energy of the Earth. It's about its own axis. Since 1957, advances in technology have made it possible for many countries, including India, to launch the artificial satellites for practical use in fields of communication and technology. We observe a satellite in a circular orbit of distance RE plus R, and from the center of the Earth RE to the radius. If m is the mass of the satellite and v is the speed, then the centripetal force observed by this orbit is mv square upon re plus h. Geostationary and polar satellites. An interesting phenomena arises if we arrange the value of r as Re plus H such that T becomes equal to 24 hours if the circular orbit is equatorial plane, such as a satellite having the same period as the period of rotation, then RH for this purpose works out to be large as compared to RE, and T is 24 hours. H works out to be 35800 kilometers, which is much larger than RE. Satellite in a circular orbit is 24 hours, called geostationary satellite. Clearly, since the Earth rotates around the same period, the satellites would appear fixed from any point. It takes very powerful rockets to throw up a satellite to such a very height that the Earth, above the Earth, that it cannot be pulled back and can perform its practical applications. India's leap into space. Thus, radio waves from an antenna can be received at points far away. Waves in a television broadcast or other forms of communication have much higher frequencies and thus cannot require uh, higher frequencies beyond line of sight. A geostationary satellite appearing fixed above the broadcasting station can, however, receive these signals and broadcast them back to a wide area on the Earth. The InSight group of satellites sent by India, widely used for telecommunication in India. Another class of satellites called polar satellites. These satellites are at low altitude, 500 to 800 kilometers, but they go around the poles of the Earth in north-south direction, whereas Earth rotates around its axis in east-west direction. Since its time period is around 100 minutes, it crosses any altitude many times a day. However, since its height h above the Earth is about 500 to 800 kilometers, a camera fixed on it can easily view small strips of the Earth in one orbit. Adjacent strips are viewed in the next orbit, so that in effect of the whole Earth can be viewed strip by strip during the entire day. These satellites can view polar and equatorial regions at close distance with good resolution. Information gathered from such satellites is extremely useful for remote sensing, meteorological as well as other environmental studies. Weightlessness. Weight of an object is the force with which the earth attracts it. We are conscious of our own weight when we stand on a surface, since the surface exerts a force opposite to our weight to keep us at rest. The same principle holds good, but When we measure the weight of an object by a spring hung from a fixed point, the ceiling, the object would fall down unless it is the subject of force opposite to gravity. This is exactly what the spring is this is exactly why the spring is pulled down a little by the gravitational pull of the object, and in turn the spring exerts a force on the object vertically upward. Now imagine that the top of the balance is no longer held unfixed to the point of the ceiling. Both the ends of the spring as well as the object move in identical acceleration g. The spring is not stretched and does not exert any upward force on the object, which is moving with acceleration g. Recorded in the spring balance is zero, since the spring is not stretched at all. If the object were a human being, he or she would feel the weight, since there is no upward force on them. Thus, when an object is free, it is weightless, and this phenomena is known as phenomena of weightlessness. Summary: Newton's universal law states that gravitational force of attraction between any two particles of mass m1 and m2 are separated by a distance r1 has magnitude F is equal to g m1 m2 upon r square, where g is the universal gravitational constant, which has the value 6.67 into 10 raised to minus 11 n meter square kg. If we have to find the resultant gravitational force acting on a particle m due to a number of masses m1, m2, m3, etc., we use the principle of superposition. Let F1, F2 and Fn be the principle of superposition, which each force acts independently and uninfluenced by other bodies. Fn is equal to F1 plus F2 up to Fn, that is summation of I from 1 to n Fi, where the symbol stands for summation. Kepler's law of planetary motion states that all planets move in elliptical orbits with the sun at one of the focal points, and the radial vector drawn from the sun to a point of a planet sweeps equal areas in equal amount of time. This follows from the fact that the force of gravitation on a planet is central, and hence angular momentum is conserved. The square of the orbital period of a planet is proportional to the cube of the major axis of the planet's elliptical orbit. The acceleration due to gravity gh is equal to gme re plus h the whole square. Gme upon re square 1 minus 2h upon re, for h less than very less than re. At depth d below the surface, gd is equal to gme upon re 1 minus d upon re. The gravitational force is a conservative force, and therefore a potential function can be defined. Gravitational potential energy associated with two particles V is equal to g m1 m2 upon r square, where V is taken from 0 to infinity, and the potential energy for a system of particles is the sum of the energy of all the pairs. If an isolated system consists of a particle of mass moving with speed v, the vicinity of the massive object B is the total mechanical energy of particle given by E is equal to 1/2 mv square, G is equal to minus g mm upon r square. With the choice of arbitrary constant, potential energy given at the point above. The total energy is negative of the bound system. K is equal to gmm upon 2a, V is equal to minus gmm upon 2a. The escape speed of the surface from the earth VE is equal to 2 GME upon RE is equal to under root 2 GRE. If a particle is outside a uniform spherical shell or a solid sphere with spherically symmetrical internal mass distribution, the sphere attracts the particle as though the particle of a mass is a sphere and a shell concentrated at the center of the sphere.